Yes, Luke.
What's homework 3 and 4 is missing?
Okay, yeah, let me ask you guys about homework in general. Let me tell you real quick here. Just this morning, I was digging through a drawer in my desk that has those sort of hanging folders. You know what I'm talking about? You know how the folder's going to hang? And when I moved a couple of the folders over, there was a bunch of homework at the bottom of the drawer. At some point along the way, I must have thought I was slipping them into the folder, but they went between the two folders and fell underneath there. So it could be one of the things on the to-do list for this morning is to go through that pile and see if there's something in the, like what's all not graded in there. Okay? I thought after that I would double check as to what all everybody's missing. Okay? Because I know that there are some grades that are not showing up in RDS yet. Okay? Anyway, so we'll figure that out because yeah, I want to make sure that if you've got it done and I've just misplaced it versus you got it done and it's still in, it's in your history folder, that kind of thing, we'll get it sorted out. Okay? Because yeah, I think that in general, don't get me wrong, I think this class is actually of the three by far the best in terms of everything is there. But we got to work on that. Okay? We'll double check. All right, and I apologize that, like I said, some of them were just laying there at the bottom of the drawer. I'm like, oh well, apparently I'm an idiot and I just missed the folder and I dropped them in there.
At least you're not like my 5th grade teacher who lost our work and then purposefully, like she never said that she lost it, even though she admitted at the beginning of the year. She did that a lot and like would tell us that we didn't turn it in.
Oh dear.
And it was like, I know I turned it in. You watched me turn it in. You asked me how I thought I did on that homework. Why are you saying I didn't turn it in? She didn't like me though. So
Oh dear.
she also didn't like that when I brought in a big tub of Legos for us to use at inside recess. I was like, no, listen, this is my tub of Legos. I get to decide who plays with them. They're not for the class. They're for me and who I say can.
All right. We have a test. I think the test will be on Tuesday. In part because that way we're spreading tests out a little bit because I know that there are people who have different tests on different days and the best I could do was Tuesday. Anyway, well, we should be in good shape by then. Today my main plan is just to kind of go through and review things or whatever. Yeah, Andrew.
On Tuesday? Or
Oh, yeah, what Monday is it?
Monday?
Is that right?
Let's
It'd
go
be
for
Monday.
Wednesday.
It's Monday then. You're right. The test should be Monday, not on Tuesday. Thank you, Andrew. The test is written already, but I mean it's a draft. I haven't copied it or anything like that yet. In its present form, there are no spreadsheet or Desmos or anything like that problems on the test. Like you don't need a laptop or anything on the test. And that's partly because there'll be plenty of times later in the semester where you have to have that. I think we can avoid a technical problem on this one. You know what I'm saying? I mean, I don't think I need to test you on like how to use the inverse function. How should I put it? We have more interesting things we can talk about inverse functions than how to do it on a spreadsheet. Okay? Whereas there'll be problems later in the semester when we're doing tableau matrices and stuff like that. Matrix tableau, I believe is how the word is pronounced. They can't be done by hand. Okay? There'll be times we have to do things on spreadsheets. Let's let ourselves off the hook a little bit on that one. So anyway, today we're just going to generally review. Okay? And there is no plan for any kind of assignment or anything like that. But here's the deal. I like to play a little bit mean in my classes, and on the day before a test, we have some kind of quiz. Okay? It counts as like a homework set. So it's not like the most important thing you've ever had, right? Because you got tons of homework sets and stuff like that, right? On the other hand, it also will help you, how should I put it, preparing for the quiz helps you know, get ready for the test, and what happens on the quiz helps you know what you do and don't know as you prepare for the exam. So plan that on Friday, because we do have class on Friday, right? Yes, we do. We will have some kind of pop quiz kind of thing, okay? What I probably will do is I'll make it very similar to the kinds of things that are on the test, but more of like a multiple choice type format, and it'll be on the website kind of thing, and then we can right away get the feedback. We can actually right up there pull up your answers and see how many people got the questions right about slope of a line, and how many people got the questions right about Gauss-Jordan.
We could have a Kahoot.
I'm ignoring MJ today because she just keeps. Yes, Luke.
Are they going to be like last year where they're open book?
I think this particular test. Let me think about that. I don't think this particular test is a big deal one way or the other. Okay, because you're right. He's asking about open book. Yes, certainly later in the semester, there are more tests where being open book will help. Okay, more like or open note. I haven't decided yet exactly because there are processes where you look things up on a table, or there are processes that we study where there's quite a lot of steps, and memorizing those steps isn't really the point. This particular test, I'm not really sure that having the book open would help. But let me think about that. Hey, I even know what I'll do. Luke, just so that you know I'm not ignoring you, I'm putting it on the to-do list is up. Answer Luke's question, read, open book in Finite Math. Let me look through the test and see. Here's the deal. Open book is a mixed blessing. Because one of the things that happens is it quickly becomes a crutch of you're not going to trust your own answers. And then you're flip. Okay? When I'm up here, I'm watching. And there's a whole bunch of people who are going to be doing that, right? They're just looking for something. The answer's got to be here someplace. Right? And then when you could have just answered it. Okay? So let me look and see what the right answer is.
I feel like if we did it like open no, and then we got to like use our homework that we did as a reference, that would, and we could get like bonus points if we stapled it for the test.
Luke?
The only reason I was asking is because I might personally get confused between which one is Gauss-Jordan and which one is.
Yeah.
Oh my. Well, let me think about that. Versus should we straighten that out between now and then?
What kind of questions Gauss-Jordan are going to be?
What can we ask about Gauss-Jordan?
Gauss-Jordan's matrix, right?
No. Gauss-Jordan is the one. Isn't Gauss-Jordan the one? Wait a minute. Now I'm confused.
It does have matrices.
Yeah, but it's in a matrix theory.
It's like you gotta solve it so you get the identity matrix, and then you have the answers because it's a modified one. There's like that line, you have the answers and you have the identity.
That is the identity matrix.
No. Well, kind of. Gauss-Jordan. Let's do a simple Gauss-Jordan
We're
one.
already confused.
All right. Now, let's actually do it the way the book actually, you know how the book really did this. The author really sat down and said the answer is going to be x equals 2 and y equals 1/2. Okay, the author already really faked this, right? And did that way. Then they come up with problems like 3x plus 2y equals 7. And x minus 4y equals 0. Am I right about that? Yes. Okay. The author really reverse engineers these things, right? They don't just throw up numbers and hope for the best. All right, so here is the problem there. In Gauss-Jordan, then, what you do is you make that modified matrix where you put your coefficients over here on one side, and you make yourself a little fence here, and then put the answers over, the right side of the equations over here. Yes?
Lisa just texted me and said that she can come to class in 20 minutes. Should she try to make it in 20 minutes?
Tell her I'd love to see her.
I think, okay.
I don't know. What's the answer? Anyway. Alright, so then what is the goal here? What are we trying to get this matrix to look like? After a whole bunch of steps, we want it to look like what, William?
Like the ones with the 1 on the diagonal.
You're going to want ones on the diagonal and zeros every place else. In this case, it looks like that. And you want something over here, because then whatever these things are over here, that's the answers. This is the x and this is the y. So that's what we're going for here. Alright, so I like to think about this in terms of how I'm going to target something here. And I know I want to get rid of this guy and I want to get rid of this guy. Alright, so let's go for this one first. I think if I took row 1 minus 3 times row 2 and made that the new row 2, this one minus 3 times this one, we'll get a 0 down here. So let's just leave the top row alone and do this to the bottom row. This minus 3 times this is 0. This minus 3 times this. Okay, that's 14. This minus 3, who cares? Closer. All right. Now, what do I want to do to get this?
Wouldn't it be negative 7? Because or it would be 7 because it's 7 minus 0.
This minus 3 times this.
Yes.
Yeah, I'll do 7.
Yep. Okay.
For row 2.
Did I do something wrong?
Yeah, you
The
put a
0.
This
Other
one
side.
here?
Yeah, what if you do
Oh, you're right. What am I thinking? You're right.
Negative.
Thank you. This minus 3 times this is 7. All right. Now we need to get rid of this guy. How about if we said this one is row 2 minus 7 times row 1? Becomes the new row 1. Because this minus 7 times this will be 0. Okay. So the bottom row, nothing's going to happen to. But the top row, this minus 7 times this minus 7 times this minus 7 times this. Negative 42?
49.
Negative 42? All right, horrible looking numbers, right? But actually it's no big deal because next all we got is got to divide this row. One of the things we can do is we can just divide a row by a constant. So let's divide this row. Row 1 divided by negative 21 becomes the new row 1. So that'll be 1, 0, 2. And row 2, let's see, row 2 divided by 14 becomes the new row 2. So 0, 1, 1/2. And remember, that was the answer we engineered here, right? We made the problem knowing... Did I make a mistake, Luke?
No.
Okay. Did you have your hand up, or were you...
No.
All right, I wasn't quite sure what was going on. All right. All right, so we have now we have, it looks kind of like an identity matrix over here on the left side of this fence. And so that means these are the answers. Here's the X and here's the Y. And we got it. Okay?
The concept makes sense. It's just when you get it on a larger scale.
Do you think on the test I'm going to make you do a larger scale?
I
think
don't
you
know.
MJ is new to Dr. Schragi tests. Am I...
I had Mrs. Webster for 3 years, so...
I'm scared to ask what, am I
don't know
evil?
how to compare. I never had Miss Webster, so.
Oh,
Yeah.
I am unlikely to make you do a problem that involves a blizzard of algebra.
Okay.
Okay? Much less arithmetic. Okay? I am unlikely to make... Would this technique have worked just as well if we also had some z's to this problem? If it had been 3 equations with 3 unknowns, or 4 equations with 4 unknowns? Yeah. But that would be a pain in the butt, right? There'd be just too much going on.
That's
So-
what I get hung up on. It's like the small ones or the ones with 3 steps that aren't too complicated to solve. And stuff.
I will double check, but I'm telling you, I don't think it's very likely I gave you a 3x3.
Okay.
It's almost certainly going to be a 2x2. What is another thing that's happy about this answer? How hard would it be, Andrew, to check your answer on this one? You would just plug those answers back in, right? Or maybe you would decide, while I'm at it, let's just do one of the methods I like substitution instead, right? Okay? It's not that hard to check your answer either. Okay? So I don't feel just too bad with a 2x2. I know there were draft questions that I was looking at where you didn't even do the whole thing. Where in teachers editions and stuff, there were draft questions where they were like, how about a thing where they just show you one step? How would you get rid of this? How would you get rid of this number and make it a 0 over here? I don't, in general, love questions like that where you just do one step. Although I see the teaching value of it. I mean, frankly, if you can do one, you can do more, and you didn't spend 15 minutes on a problem. Okay, so I see the value of it. I don't tend to ask that, but you could. What was the purpose of Gauss-Jordan again? What were we doing? Solving, says Malia. Solving what?
X and Y.
Solving for x and y. Solving systems of equations. Remember, the first part of this book was just about making graphs of equations and so on, which wasn't that big of a deal. I mean, you're all survivors of classes where you've done that to death. And when you had something up here like 3x plus 2y equals 0 with a little rearranging, you could show that that's a graph of it. And you had a second equation and you could show that that's a graph of it. And when we say solving, it's so easy to lose track of this. To lose track of what this even means. What you're really doing is you're finding the values of x and y that make both equations true. We need the total number of coins to add up to 10, and we need there to be whatever, this many copper ones and this many shiny ones or something like that. And the only answer that works out to both is this right here. This value of x and this value of y solve both. That's what we mean when we say we're solving these equations. And we have a whole plethora of tools at our disposal to do this from all through our education. Yes?
Are we ever going to do anything, because going off of that, are we ever going to do anything involving sigma?
What was sigma?
The sum of...
Oh, yeah, well, you did that. Okay, we'll get there.
Okay.
Yeah, okay. So, we had tools to do this. I can't even remember. What did your book call the first technique we learned? Was it elimination or substitution? What did they call it? I mean, in many ways, for simple methods, it's kind of the same thing, right? I mean, if we go back to 2.1, notice I'm so far kind of ignoring chapter 1.
It's echelon. I think that's all I have written down.
Yeah. Oh, they called it the echelon method. Right. Okay, so what they did in the echelon method is they took something like this, which is not the hardest problem in the world. I guess you can already look at it and tell the answer is going to be x is 1 and y is 1. But whatever. What did they do in the echelon method? They just did the same kind of row operations that we did in like Gauss-Jordan, but they were trying to get rid of just this one right here. So like if we said, how about if we took these equations and we said this one right here, we're going to take this one minus 3 times this one. So we're going to replace this equation with this one minus 3 times this one is 0x. This one minus 3 times this one is minus 2y. This one minus 3 times this one is negative 6. So our new equations were 3x plus y equals 4 and negative 2y equals negative 6. And the idea was, well, now there's once you have this sort of upper triangle, similarly if we had z's in this equation, you want it to be this upper triangle thing in echelon method. Okay? Because then all you've got to do, okay, now you have an answer for z. With a little bit of algebra, you have an answer for z. Plug that value in for z right here, and you can get a value for y. Plug those values of y and z into here, and you get x. I don't know if you happen to remember, but there was a nifty word for that. That's called back substitution. Back substitution was that method where once you had the bottom run of that echelon table there, you could then back substitute and work your way back up the table and get all the answers. Okay. But that echelon method, I forgot that was the word they used for it. That echelon method, well, it's a bit tedious. We're bigger than 2 by 2. Okay? And at 2 by 2, it's basically the same thing as words you used in pre-calculus like substitution or elimination. I mean, they're all kind of equivalent when it's just a 2 by 2 matrix, right? Okay. Then we also had this one that we did, Gauss-Jordan. That was another way to solve systems of equations. And we spent some time on that. And then there was, well, we spent actually 2 lectures on addition of matrices, which nobody was worried about, and multiplication of matrices, which I don't think anybody was worried about once they remembered it. Right? It's just a technique.
Actually, can we, if we think about using our nestle list, because I have to look at my notes every time I do the multiplication. Like, I just get so confused.
Okay.
Because I don't know what
I
to
do
like
too.
add and I don't know what to multiply.
Really?
Yeah, it just kind of becomes like a blur.
Okay.
I can understand that.
Okay. All right. Well, that's good information to have. Let me think about whether we would want then. Okay. So you're saying.
Like, if we have like two matrices like this, when I go like A times E, but like I don't know if I should like, I don't know if I should add the B times G or like if that's together or not.
Okay. So if you have some matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you want to multiply it by, I've kind of worked myself into a hole here. 2, 4, 6, 8, 10, 12, 14, 16, and 18. All right, first off, can we multiply those two?
Yes.
Absolutely. It works best if you actually write out, this is a 3 by 3 matrix, 3 rows by 3 columns. This happens to be 3 by 3 as well. As long as these two numbers match, you can do it. And the result will have the dimensions of these two, in this case 3 by 3. So it works. All right, once you know you can do it, here's how I remember. To get my new matrix, I know it's going to have 3 by 3. The question is, what's in each of those boxes? All right, so here is row 1, column 1. I use row 1, column 1. Then it's this times this, plus this times
So
this.
all of them go in. Okay.
Yeah, any of them would work. I don't know if I have a marker here that
row
works.
one, you do row 1 times column 1, column 2, column 3, and then row 3 times column 3.
I think I understand what you mean. Let me just show you. So like, let's say I wanted to do this one right here, row 1, column 3. I use row 1, column 3.
Okay. So sometimes, like, if I did like the row and column one, I would just do like the 1 times 2, and then I wouldn't know.
Oh yeah, keep going. Yeah, absolutely. Let's do this one right here. Row. Oh, this is
The
a
ones
good
that
marker.
confuse me are the ones that aren't the exact same, but they have different amount of rows and columns, but they still work.
Yes, let's do one.
That kind of confuse me.
Let's do one like Luke was talking about. That is a great idea. How about 1, 2, 3, 4, 5, 6. So this is a 3 by 2 matrix. So I'm going to need a 2 by, how about 2? 1, 5, 6, 7. These two match. The number of columns matches the number of rows over here, so it's going to be fine. And the result is going to have 3 rows and 2 columns. So it's going to have 3 rows and 2 columns. So to do, let's just say row 3, column 1. We're going to use row 3, column 1. Row 3, column 1. Do this. 41. Or, have a different color. How about row 2, column 2? Row 2, column 2. 28, 38, 43. Okay? Yeah. No, I agree. I actually think it always takes a little bit of thinking to remember this. If you think having the book or the notes open about that, again, let me look through the test and see if I agree. but gut reaction is, I mean, that your input is valuable on that, okay? Yeah, Luke.
And then to figure out how many rows and columns will be in the last one.
Uh-huh.
What do you?
It's the outer, so if you wrote down, remember you always write a row, column. So wrote down the first one, number of rows, number of columns. Write down the second one, number of rows, number of columns. The result will be the outer.
So.
You'll have 3 rows and 2 columns.
Okay. Cool.
Yep. Yep, there's a pattern to it, isn't there? Yep. Okay. So, okay, we have those multiplication of matrices, addition of matrices, subtraction of matrices. No big deal. Now we learned that there are also such a thing as inverse matrices. Not every matrix has an inverse. For one thing, it has to be a square matrix. But even not all square matrices have inverses. In fact, that's kind of a thing in math. Figuring out, it's one of those big problems in math, is figuring out, I give you a 47 by 47 matrix. Can you figure out if it has an inverse? In theory, but it's a pain. Okay? In general, it's hard. There were a few things they warned you about, like watch out for matrices that have a whole row of zeros or a whole column of zeros, that kind of thing. Watch out for 2 matrices that have 2 rows that are the same, or 2 rows that are just a multiple of the other. Like this one is 1, 1, 1, and this matrix, this row is 2 by 2, 2 times 2 times 2, 2, 2, 2. Okay, but I'm not going to give you anything crappy like that. If you have a matrix A, let's just say it's 1, 2, 3, 4. There is a matrix, there might be a matrix A inverse out there, and I'm not going to try to even guess, bloop, 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 something. And what is amazing about A and A inverse? If you multiply them together, they equal the identity matrix, which is 1s down the diagonal and 0s every place else. That's the identity matrix. That makes A inverse kind of, multiplying by A inverse is kind of like dividing by A. Okay? In the same sort of way that if you had AX equals B, X equals A inverse B, where we meant A inverse as in like 1 over A, would be a thing, right, in algebra. It'd be a kind of clumsy way of doing it, but it would be a thing. In the same sort of way, if I have some matrix A multiplied by something called, let's say, X equals B, that's a matrix, that's a matrix, that's a matrix, X equals A inverse B. Lisa, it is good to have you.
Sorry, I woke up so late.
Here's some homeworks. I was just telling them earlier that I found some homeworks that were missing, and so I haven't graded them. About just like an hour ago I found them. So if I don't know that one of them is yours, but if you have some missing spots in the grade book, it's possible they'll get filled today. Okay. All right. So this A inverse thing is a neat thing. We're just reviewing. Okay. It is a handy thing to have. Doing it by hand is a pain in the butt. But it is more exercises in doing row operations on matrices. I'll have to admit, I wrote the test for this class, that test that you'll take on Monday, literally like 2 weeks ago or something like that. I have to go back and look. I don't remember if I actually made you do a matrix inverse by hand or not. But it isn't really that big of a deal, remember? I mean, we just put our new friendly matrix over here that we're trying to find its inverse of, make ourselves a little fence to help us remember, and put the identity matrix on the other side of the fence. And then we do a bunch of row operations until we get it so that we can have the the identity matrix on this side and stuff over here. And this stuff is the inverse. It's not that hard, it's just that it's time consuming. And I don't love time consuming questions on a test because it can be easy to misjudge how long, if it took you 20 minutes to do that versus it took you 5 minutes, totally blows how you do the rest of the test, right? So I'm inclined to say I don't suspect you're going to have to do that, but wait until Friday when you have a more formal review sheet and all that kind of stuff. Okay? I don't think it's very likely, though, that I would actually make you do one of those by hand, especially since I've already shown you that there are, like spreadsheet ways of doing it quite easily. And matrix inverses are super handy because they are, in many ways, the giant, handy way of solving systems of equations. Wait a minute, hold on a second here. Yes, you can come in. What's up?
Oh, I just had a question about
Yep.
this.
Okay. Is there a mistake on it?
No,
Okay.
I just didn't understand how to do it.
Oh, okay. Okay. So, are these questions about the range and the domain?
Yes.
Okay. You know what? You are welcome to open. I don't know if you have your book open or not, but you're welcome to open up the book and talk and look what it says about the range and domain of a function and of its inverse.
Okay.
Okay. But you're certainly welcome to see, like, how is the domain of function f related to the range of inverse of f? Or is that inverse? Was that the right word we used? Yeah, the inverse function. Yeah.
It is N.
Okay.
Alright.
Yep. All right. Yeah, that's okay. And if you don't know, that's all right. That's part of the.
What section am I?
That's probably 1.6.
Okay.
Whatever was the one that's called like inverse functions or whatever.
Alright.
Okay? And if you still can't find it, come on by. Okay? He's so nice. Okay. In many ways, it's the best. This inverse function way of inverse matrix way of doing it is the best. It unfortunately is a pain in the butt to actually get those inverse matrices unless you have a tool like a spreadsheet. Okay? But if I had some big system of equations, 3x1 plus 2xy, x2 plus 3x3 plus x4 equals 7, x1 plus x2 plus x3 plus x4 equals 0, 2x1 plus 2x2 equals 8, and x2 plus x3 equals 17. I've got 4 equations with 4 variables. Does a solution to this exist? Maybe. She said yes. She said yes. In general, that's a good bet. If you have the same number of equations and the same number of variables, most of the time you're on the road to success. Okay? What happened if there had only been 3 equations? Almost certainly there's not a single answer. Almost certainly there's a whole mess of answers. Okay? Like you could pick any value of x1 and then there would be values of x2, x3, x4, but any value would have worked for the first one. Well, most of the time in the real world, that's not how problems... Remember, finite math is fundamentally about finding problems for the real world. Most of the time, if you're trying to find the right number of cupcakes, cookies, pies, and donuts to make at your bakery, there is a right answer. There isn't an infinite number of right answers. There is a right number. Okay, that is the best, or whatever. I don't plan on giving you a problem where there's like not a solution. Yeah, because what if there had been one more equation? x1 minus x4 equals 12. Now what? I got 5 equations with 4 unknowns. There's probably no answer at all. There is no combination. If you have too many equations and not enough variables, most of the time the problem is over-constrained and there's in fact no answer at all. But I wouldn't in general do that to you. In general, I would make it like this. So that you could make this 3, 2, 3, 1, 1, 1, 1, 1, 2, 2, 0, 0, 0, 1, 1, 0 times x1, x2, x3, x4 equals 7, 0, 8, 17. This is a matrix equation. We can call this A, we can call this big X, and we can call this B, as the worst B ever. AX equals B is an equation. And it's a bit of abstract algebra to show that in fact it's not only the same equation, but all of the properties that seems like it should work will work. Like, we should be able to solve for x by just moving a over to the other side. But we don't have the operation of division on matrices. Again, that's a delightful little bit of modern algebra that you would have to learn out why that is. But the idea that, hey, we got the inverse matrix, we can just do this. Effectively, what we've done is multiply both sides by A inverse. Well, A inverse times A is just the identity matrix. That didn't hurt anything. And A inverse on this side times B. Now, finding A inverse of this would be a pain in the butt. I can't say that the final draft of the test will have it. I know there were draft equations that I typed up where I give you A inverse. Okay? Because that would just be too clumsy for you to actually... I mean, again, no, you could do it. It's just that you have a finite amount of test time. So then, if I gave you that the A inverse matrix equals whatever, this is suddenly so easy. It's just a matrix multiplication. And finding A inverse is hard, but computers can do it before your finger is off the enter key. When you typed M inverse, right? By the time your finger's off the key, the mere fact that there was a million math calculations involved, who cares? Right? You don't care. That's why the computers are going to someday have an uprising and take over the world and get you. Because you were being mean to them, making them do all this math. I think it's the other way around. I think the Mac computers are happy when you make them do math, but that's another story. So this only becomes easy. But we learned in the class why this is better. Not only is this pretty easy once you have A inverse, but it's a reusable answer. Because if they then have another problem where the same thing happens except you just have different numbers over here, all you did is change these numbers. So you just but the A inverse is still the same dumb thing. You just multiply by this and you have a whole new set of answers. You could not have done that with any other technique we learned. Echelon method, Gauss-Jordan, all of them would have been start over. This isn't start over. This is just, you just reuse your A inverse matrix and you have the new B and you get new answers of X and you look so smart. Because you've solved a new problem. Wow. So this is definitely the king of all best possible ways to solve these sort of problems. But you gotta have those A inverse matrices. But that's okay. You now know that there are techniques to do it. And I think that's as far as we went with that, except we did one more matrix thing.
If we do, for the test, are we going to have to do things on spreadsheet?
No, I was talking about that before. I think this time around, there will be plenty of other tests in the class where you have to use a spreadsheet. Like when we do optimization with matrix tableau, there's no way to do that without a spreadsheet. You can't do the math by hand. And so I think because this time around, I think we can do this without spreadsheets. Okay? And that way that gives everybody time to be more comfy with their spreadsheets and have more time with Mr. King and have more time with Mr. Draghi and all that kind of stuff to get all comfy with it, okay? That sounds terrible. It sounds, do you know what I'm saying? To be more comfortable and faster.
Yes, sweetie.
Yes. Did Jacob tell you I called him sweetie, or did I tell you that?
You told me.
I'm sorry.
We talked about it though.
Oh my gosh, I am just so embarrassed. Anyway, all right, we did do one other thing though with matrices, and that was the graphics transformations. The ones that have come in already look nice. I don't think I saw anybody get it wrong. I do remember now that on the current draft of the test, it says something like, write some questions about graphics transformations here. So there's no questions yet. We'll have to figure that all out. But they weren't really, I mean, how should I put it? You guys are going to look so smart on that part of the test. I'm going to take these tests and go over to the math chair over here in Ivy Tech and I'll be like, look at how smart my students are. Because you guys are going to be like doing all this awesome stuff. I mean, if you had some, no matter what, it's all about working with shapes, polygons. And polygons are just sets of points. If we have a set of points that makes Pac-Man, all he is a set of points. These vertices, each one of them here has some coordinate x1, y1, and this is x, let's say 5, y5, all the way up to, I know this one, xn, yn. But they're just position they're just positions of those coordinates. We just start with Pac-Man right here. And in fact, Pac-Man, is just a matrix where x1, y1, x2, y2, all the way out to however many position it takes to describe him originally. This is the basic set of points that describes Pac-Man.
Okay, but is that more like, especially like old arcade games, if they're so pixely?
It's a complicated set of other problems. These are more like vector games. Like when we looked at asteroids the other day, the asteroid was clearly made of line segments that were each individually quite well drawn, not necessarily very pixely at all. Old arcade games were done with what's called sprite graphics, and that's not really what's done anymore. That was when there was like a little grid of like, it was also a matrix. Oh, I love that. You're bringing out the old Commodore 64 programmer in me. But you're right. Old video games might have had a kind of a different thing where they made a little grid, maybe 8 by 8, and like they have colored in parts of that little grid to make the shape of Pac-Man.
Yeah.
It's like a grid, and then they just move that little grid. And so he makes a very pixely, weird old thing. That's how like old school video games were done. Modern video games are all done using this kind of vector graphics where they're connecting polygons.
No, I was just
Old school stuff though, yeah. You're playing Galaga
Yeah.
at the video arcade with your nickels or your quarters or whatever. It's old school sprite graphics. That's done totally different.
I'm asking because I grew up going to a pizza place that was also an arcade, and there was like all those old games.
My 8-year-old is currently on an old school video game kick. He'll tell you about how much he hates video games, but he does like old school Defender, Galaga, Pac-Man type
There
games.
was like a simple goal in mind and stuff. It wasn't like you have to do 500 side quests
Yep.
and maybe you'll finish.
Alright, so here's the positions. To put him on the screen where you want him involves transformations. One was to translate him to a different spot. Translate, to slide him over. And that was just an addition operation. However far you want to move him over to down the x-axis, and however far you want to move him down the y-axis is you just added. We're going to move him 4 down the x-axis and 7 up the y-axis at this moment. And you just add as many 4s as it takes to have a matrix with the same shape as your original, and as many 7s as it takes to have the same number as you had before. But it's just a matrix operation like that. It's just an addition. And in fact, that's what the game is doing 30 frames a second. It's now moving him 4.1, 4.2, 4.3, or whatever, however far, to animate him as he moves along.
It's just like, it's so, I don't know, it's so weird to think that like programming is a thing. Is that weird? Like that video games like are so like...
Advanced?
Everything is so much thinking to think that all of it has to go granted. Yes.
Who programmed this? And who
So
figured it
many
out?
very bright people. Oh my goodness.
Yeah, they're way smarter than
Oh my God, did you say that?
you. And
Lisa, you have my permission to do whatever you want to Luke for the next 20 seconds. Go!
well, she's,
Because
she
I
already
decided
blocked my
like
phone
what I
before.
want to do in the future, which is you know what a cryptographer is?
I do.
I really want to do that, but
Oh, it's awesome.
it sounds hard.
I think. Alright, another thing we can do is resize him. Now, that doesn't happen in Pac-Man. Okay? He's just a little. Actually, in fact, in real Pac-Man, it's sprite graphics, but whatever. Okay, but you know, we can imagine the game could change where like Pac-Man gets bigger or he gets smaller. We could multiply him by something to scale him up. And in practice, that's just a matrix multiplication. In fact, it's kind of like multiplying by the identity matrix, except multiplying by the identity matrix does squat. You need to multiply it by some multiple of the identity matrix, like 1.1. so that you are increasing him, he's now 10% bigger than he was before. Or 11 times bigger than he was before, or whatever. Now, correctly, on the other day when we did this, people realized, wouldn't it have been easier to just do a scalar multiplication and just multiply him by 11? Yes, that would have. And in practice, my guess is most of the time behind the scenes at Pixar, when they're making computer graphics, or in some video game company, that's probably what they're really doing. But we teach it this way because you wouldn't necessarily have to scale it the same amount in both directions. If you wanted to stretch Pac-Man out 2 in the X direction, but not in the Y direction at all, so that now Pac-Man looks like this, you could do that. You are multiplying him by a different scale in the X direction than in the Y direction. And then you could translate that by adding some amount of X and some amount of Y to put him someplace else on the screen, so that now he's over here. We also talked about the fact that you could rotate him. Now, the rotating took a little bit of trig. Because that rotation matrix, you had to know the angle you were going to rotate him. Let's say theta. And then there was something like sine theta and minus sine theta, cosine theta, minus cosine theta. I forget exactly. Once upon a time I actually knew it. But once you... What did you say?
That's some crazy looking Pac-Man.
Yeah, I know. He looks totally weird, doesn't he? But you could multiply them by that rotation matrix. Let's say we rotated him 10 degrees, and now he looks like this instead. Right? And then we rotate him another 10 degrees or something, and now he looks like this. And you could have some animation where it goes as he turns around.
Doesn't that happen whenever he dies?
Yes, again, it's really sprite graphics. It's not really vector graphics. We have boing, boing. Boing, boing. Yep. Yes. Every device in our house, every little phone and tablet in our house right now has stupid 80s games downloaded for free from the Play Store. And they're all full of ads, and God knows what kind of cryptocurrency mining software my child is inadvertently installing on our tablet. And God knows what, yes.
So like if you have a question with the rotating it, will we have to memorize our
No, I won't ask you a question that involves you have to know that trick of how to do it. Okay, that's not such a big deal. I don't care about that.
We should take a field trip to the arcade down the street.
Yeah.
Arcade.
No, you know what we need?
Yeah, it's
We need those new badass tablets that they have. You guys seen those? When you ever go back to your homeschool? So the Promethean boards, right? Have you seen them being replaced by those 8-foot diagonal Android tablets?
Yeah.
Wait, what?
They're like Android tablets, almost as big as this screen.
But the last one.
And they're real Android tablets. I mean, they're just like big OLED tablets.
We would never get anything done though because we just load up the Google Play Store and we're like, so what do you guys
I know,
want
you
to
can have
play
so many
today?"
things. I know, we totally need them.
I need to get Galaga on my phone.
I have not found a good Galaga. My Galaga is the current favorite of my 8-year-old. And so far, we haven't found any good clones of it for free.
Galaga's
I have an N64 and a PlayStation 2 that has a combination of all those old games, so I just put it on. I prefer playing it on the N64 though, even though it's we got a really nice TV.
Yes, I love whenever we have I think it's for my. I think it's our Nintendo 64. You can plug it in and it's like a little console thingy. And it's like the arcade. Those are so much fun. We have 10 of them at home.
Oh my gosh.
You gotta blow into
Luke,
the cartridge.
I just want to tell you a little fun fact.
Fun fact from Luke.
Okay, so I work at Walters, and there's this guy that comes in every once in a while. We call him Galaga Man, because he'll put one coin in, or he'll swipe it one time, whatever, but he'll stay and play for 3 or 4 hours.
No! That's
Every time.
holy smokes, I think there was a song about that. Anyway, that's cool. I didn't know you worked at Walters.
You know that Bob's Burgers episode whenever he gets a
Oh my
that
gosh.
game and then he gets at high school and he goes and saves and then he goes to the arcade, he brings his kids and then he gets kicked out for trying to find them.
Now,
What are you
All right.
on about?
I love Bob's Burgers.
when we look back at chapter 1, I think chapter 1 Section 1 and Section 2 are going to be no problem. I could be wrong, but that's just like slopes of lines and stuff like that. I suspect you guys will be fine on that. Well, no. Yes.
Will you ask questions like, can you put this in standard form?
Maybe.
Okay.
I'll be honest. I'm having a hard time in my brain keeping this test straight from the pre-calc test. Because the chapter 1 of this was very much like the first 2 or 3 sections of pre-calc. And so I have to admit I'm having a hard time remembering which test is which. There certainly were questions on one or the other of the tests. There were of the form like, y equals 3x plus 1. Rewrite in standard form. Okay, well that would be negative 3x plus y equals 1. Rewrite it, or take this and rewrite into slope-intercept form, or whatever, okay? Whether that was this class or whether that was pre-calc, you guys should be able to do that. I'm not really that scared. I am a little bit unsure about the lecture that was the correlations and regression type, the least squares line.
Yes.
Yes. Okay. There's limited things we can do with that on the format of a test. Okay, we can't. Hey, Luke, you were asking about what was homework 3. Homework 3, I think, was the one that was about those regression lines. It was a spreadsheet one. Let me double check. There was a homework set where you did this. Yeah.
Yeah, those aren't on mine either.
Okay, so it could very well be that that didn't get graded. Like, I'll need to double check. You know
No,
what?
that's the one I probably
that's-
would most
All I
likely
know is
do.
I've turned in every
Homework 3 in Finite Math. Yes, it could very well be. I had the folks in pre-calc share some stuff with me on Google Drive, and it created an avalanche of Google Drive notifications. As they, no, in a happy way, but it could very well be that that was when you guys did that assignment, and they're buried in that. Because I can just drag those all off to a folder. I didn't actually need to look at every single, well, I opened them, but I mean, I didn't have to like save them and print them and lovingly cherish each piece of crap, that pre-calculus students sent me.
Honestly, it sounds like a headache.
I know, I don't want to be making that mistake again. Anyway. Alright, so here's the deal. What can I ask you about that? Okay. Here's some data. Maybe X here is age, and Y here is height. And we're looking at kids from lots of different ages, all over the school district, and we're seeing that each spot here represents a kid, and their height. In general, I think we would agree that it sure looks like as they get older, they get taller. Well, I mean, in this particular case, that makes sense, right? As long as they get older, that sounds terrible, but I mean, there's a least square, there's a best fit line here. If the child is older, we would expect him to be taller than another child who is younger, right? If we had some age, we could guess what his height is. I mean, we'd be wrong, because few, if any, of the child are exactly on the line, but they're all as close as possible to the line. Here's a really short old kid, here's a really big Hulk of a young kid.
I'm like below the line.
Oh my god.
Me too.
Would you believe I'm the tallest of the Shrunky family?
Are you serious?
Yes, it's crazy.
What do you have, like midgets?
Thank you. We're all very...
No, my mom's
You
like...
insulted my midget family?
No, my
I'm
mom...
going back to the circus now.
But my mom's
My mom's like one of the tallest of her sons.
Oh my goodness.
And she is only 5'3". She was taller, but then she had a car accident, and things happen.
Alright, what do we need here? What would tell us something about this? This was the so-called least squares line. It's a very common technique to figure out a best fit line. And we need some pieces of information to describe that line. What kind of pieces of information do we need to describe some kind of line? Its slope and its intercept, right? Alright, and both of those things was a thing in section 1.3. There was the slope of the least squares line, and there was the intercept of the least squares line. And they involved terms like sigma x, or sigma x squared, or sigma xy. What were those terms? Like, Lisa, because you're well rested.
Oh, no, I got like 3 hours of sleep. That's why I woke up late.
Tell me, what does sigma x mean?
Isn't that like the sum of all the x's?
That's right. This was based on some table of data. X's and Y's. The X's were the ages, right? I mean, these kids each have some age. Whatever their ages are. We just added them up. What is sigma x squared? Malia, what is sigma x squared?
You take the whole column and then you squared everything.
Yeah, we just squared each of these bad boys. And then added up those squares, right?
Can you add up then square?
Nope.
What?
Nope, you cannot add then square.
That's what I've been doing.
Sum of x squared is not the same thing as the sum of the x's squared. These are not the same thing. Let us test that. Here, Lisa. 1, 3, 5, 7. Let's say those are all the points we got. Sum of the x's is 4, right? Sum of the x squareds is 10. If I had taken the sum of the x's and I had just squared it, I'd have gotten 16, right? They're not the same thing. What is sum of xy? What is that?
X times y.
X times y,
And then add them.
and then sum those bad boys up. That would be sum of xy's. Okay. There's a number that describes how well that correlation coefficient worked. I'm sorry, how well that best fit line worked, that least squares line. It's called R. Your book used the term, I believe, coefficient of correlation, which is a little bit like dragging fingernails across the chalkboard for me, because as a stat, do you guys know my undergraduate degree is stats, and that hurts me because that's not the right word for that term, but that's another story. All right, R is the correlation of coefficient, apparently. Malia, should the coefficient of correlation be a positive or a negative number here, or of course a 0?
Positive.
Right, and how'd you know?
Because the slope's going up.
Yeah, the coefficient of correlation, which describes how well the least squares line fits, gets its sign from the slope of the least squares line. Okay? What is a range of values that the coefficient of correlation can be? Well, how low can R be? -1. How high can it be? That's right. So it ranges from -1 to 1, but big negative and big positive numbers are both fine. -0.9 and 0.9 are both fine correlations. Because the sign, remember, just has to do with the slope of the line. Okay? So that's no big deal. Is this a pretty good correlation or a pretty lousy correlation? It looks pretty good to me. I mean, they're kind of all clustered around here, right? I mean, a really crappy correlation is when you can't even really see any pattern at all. I mean, are you going to put a line this way or put a line that way? This thing might have a correlation quite close to 0. This thing might have a correlation of like maybe 0.8 or something like that. It's a fairly close number, but it's sort of an eyeball thing. Okay, you'd have to actually compute it to get a sense. But the closer they get to being on a line, the better and better the correlation coefficient gets. Maybe this would be 0.95 or something like that. Okay, they're getting pretty darn close to being on there. All right. We will review more on Friday, but between now and then, you need to take an exit ticket. Oof. Hold on, let me
Will the questions on there, because I don't have the, will it be solved for the least squares line, because I don't have the
Nope.
formula right?
Nope.
Great.
Okay, you should have Finite Math loaded up.
Well, you got one.
It should be available for you. Quick little exit ticket.
Pretty cool. Is it low or is it like the last one?
I don't remember.